Hello and welcome back to Math 1324. We are starting Chapter 8, which is probability. And the first section we're going to look at is sample spaces, events, and probability. To talk about experiments, we need to talk some definitions first. An experiment is an activity or occurrence with an observable result. So some examples of an experiment would be flipping a coin, rolling dice, observing the frequency of defective items maybe from an assembly line, observing the frequency of deaths in a certain age group. Those are all experiments. You can watch the activity and have an observable result. Number 2, experiments that do not yield the same results each time they are performed, no matter how carefully they are repeated under the same conditions, are called random experiments. And we will consider all of our experiments from this chapter to be random experiments. Number 3, each repetition of an experiment is called a trial. So every time you do the experiment, each repetition is called a trial. The possible results of each trial are called the outcomes of the experiment. Okay, some more definitions about sample spaces and events. The set of all possible outcomes for an experiment is called the sample space for that experiment. An event is a subset of the sample space. So the sample space is all possible outcomes, and we're going to talk about events, which are a subset of that sample space. We say that an event is simple if it has only one outcome. Otherwise, the event is compound. Okay, let's look at some examples. If our experiment is tossing a coin and observing heads or tails, so we're going to start and we're going to toss a coin. We can either observe head or we can observe tails. So our sample space is just heads and tails. Okay, what is the event of tossing a head? That event would just be H. Okay, number 2, our experiment is tossing 2 coins and observing heads or tails on each coin. So we're going to toss the first coin. If we got a heads on the first coin, and then we toss the second coin, we could either get heads or tails. So one event would be that we have H and then H. Another event is that we could have H and then T. Another event, if we had tails first, we could have tails and then heads or tails and then tails. So what is our sample space? Our sample space would be head, 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 tail, tail, head, or tail, tail. That's our sample space. That's all the possible outcomes we could observe if we tossed 2 coins. All right, what is the event of at least one head? Okay, of all of the possible events, which ones have at least one head? It would be those 3. So we would write down the event head, 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 tail, or tail, head. That's the event of at least one head. All right, what's the event of 2 heads? Exactly 2 heads. That event would be head, head. All right, example number 3. The experiment is spinning a wheel of numbers between 1 and 6 and observing the number that the pointer stops on. So here's your spinner, and you're going to spin that little spinner and observe what number that spinner stops on. So the sample space, all possible outcomes, it could be a 1, 2, 3, 4, 5, or a 6. That is my sample space. Now the first question, what is the event that the number is odd? So from my sample space, which ones are odd? It would be, the event would be 1, 3, 5. All right. What is the event the number is even? Well, that would be the event 2, 4, or 6. What is the event the number is divisible by 3? So which numbers in the sample space are divisible by 3? It's only 3 and 6. Okay, number 4. Your experiment is rolling a 6-sided die and observing the number that lands facing upwards. For this example, what would face upwards is a 6. So the sample space, you've got a 6-sided die. They all have a different number of dots on them, and the number of dots range from 1 to 6, so that's your sample space. The event of rolling a number less than 3, the numbers less than 3 would be 1 and 2. What is the event of rolling a number that's divisible by 3? Well, the only ones divisible by 3 are 3 and 6. Hey, example number 5. Your experiment is now rolling 2 6-sided dice and observing the numbers that land facing upwards. So you're going to have 2. It's easiest on this one for your sample space to think of it as an ordered pair. So you have the first die as your x coordinate and your second die as your y coordinate. This would be the event 2, 4. All right, so if we think about it, we've got 6 dice, 6 different outcomes on the red die and 6 on the blue. So there we go. Your sample space has 36 ordered pairs in it, and they are all listed. I'm going to grab a pen. They're all listed up there. Those are all the elements that are in the sample space. Okay, what is the event of rolling a sum of 4? Up here, which ones add up to 4? 1 plus 3, and then you also have 3 plus 1, and 2 plus 2. I think that's it. So a sum of 4, that event would be 3, 1, 2, 2, and 1, 3. Okay, let me delete that. What about the event of rolling a sum of 11? How could you get a sum of 11 from that sample space? You could do 5 plus 6 or 6 plus 5. That's it. Okay, so that event would be 5, 6, 6, 5. What is the event of rolling a double? And a double means the same number on both dice. So the event of rolling a double, you could have a 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, or 6, 6. So the event of rolling a double would be a 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, or a 6, 6. The event of rolling a double. Okay, what's the event of rolling a sum of at least 11? Okay, we've got to remember what at least 11 means. It could be 11, which was 5, 6, and 6, 5. Or it could be anything bigger. Well, the only thing bigger would be the 6, 6. So the event of rolling at least 11 would be 5, 6, 6, 5, and also 6, 6. Okay, now we're going to talk about simple, certain, and impossible events. Some definitions. An event with only one outcome is called a simple event. If that event only has one outcome, it's a simple event. If the event equals the sample space, so the event has everything in it that's in the sample space, then we say that that event is a certain event. If the event can never occur, in other words, the event is the empty set, then we say that that event is impossible. If it can't ever occur, it's an impossible event. Okay, an example. If you roll a six-sided die and observe the number facing upwards, what's the sample space? Our sample space would be 1, 2, 3, 4, 5, 6. Okay, so I'm asking, what is the event of rolling a 2? That event would be 2. Is this a simple, certain, or impossible event? How many things are in that event? There's just one outcome. So this is a simple event. Okay, next question. What is the event of rolling a 7? Okay, from our sample space, there is no 7. That event is the empty set. You can't roll a 7. It's impossible. It's an impossible event. Okay, what's the event of rolling a number less than 7? Well, what ones are less than 7? 1, 2, 3, 4, 5, and 6. That event has the same elements in it as the sample space. So this is a certain event. Now let's go talk about probability. Definition: given a sample space that consists of event 1, event 2, all the way to event n, we're going to say that that sample space has n simple events. And to each event, we're going to assign a real number denoted by the probability of event E, and in this case is going to be sub I. So the probability of event 1, the probability of event 2. So we can assign a number called the probability of the event for every event in a sample space. Okay, there's rules to that though. So an acceptable probability assignment must satisfy the following 2 rules. The probability of a simple event has to be a number between 0 and 1 inclusive. The probability of every event has to be a number between 0 and 1. And the second condition, the sum of all the probabilities of all simple events in a sample space has to add up to 1. If you add all the probabilities of the events in the sample space, it has to add up to 1. So my examples are the following an acceptable probability assignment. So the experiment is tossing 2 coins and observing heads or tails on each coin. So what is that sample space? If you remember, it's head, 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 tail, tail, head, and tail, tail. There were 4 events in that sample space. Okay, are these acceptable probability assignments? We see the simple events listed up top. They're all different. Okay, we've assigned numbers to all of them. 0.5, 0.25, 0.25, 0. Are all the numbers that we've assigned between 0 and 1? And the answer is yes, they all are. They're between 0 and 1 inclusive. Now, if we add all those numbers up, 0.5 plus 0.25 plus 0.25 plus 0, what do we get? 0.5, 0.25, 0.25, 0, we get 1. So yes, that is an acceptable probability assignment. All right. The second one, 0.5, that's the exact same. All right, let's go change it. What if I had 0.5, 0.2, and 0.2? Would that be an acceptable probability assignment? They're all numbers between 0 and 1, inclusive, so that's good. But if you add those numbers up, 0.5 plus 0.2 plus 0.2 plus 0, you get 0.9. That is not equal to 1. The probabilities all have to add up to 1. So this is not an acceptable probability assignment. Another definition, probability of an event E. Given an acceptable probability assignment for the simple events in a sample space S, we define the probability of an arbitrary event E. So we're going to denote that the probability of E as follows. If E is the empty set, we say the probability of the event E is 0. If E is the empty set. If E is a simple event, the probability of E has already been assigned. But if E is a compound event, if it has more than one outcome in it, then the probability of E is the sum of all the probabilities of all the simple events in E. And last but not least, if E is the sample space, then the probability of E is equal to the probability of the sample space, which is 1. Okay, we're going to go look at some examples. The experiment is rolling a 6-sided die and observing the number that lands facing upwards. If you haven't seen it by now, you're going to know these sample spaces. The sample space would be the numbers 1 through 6. Okay, what is the probability of rolling an even number? Well, first you have to get the event of rolling an even number. What is that? It's going to be the event of 2, 4, 6. Okay, I'm going to go back up to the sample space and have define a probability assignment. So here's the event. Here's the probability of the event. Okay, I can roll a 1, 2, 3, 4, 5, or 6. If we're under the equally likely assumption, the probability of rolling a 1 would be 1 out of 6. And for each other number, they're all 1/6. That's assuming you have a fair, unweighted die. If you add all those probabilities up, you get 1. So that is indeed an acceptable probability assignment. Okay, what is the probability of rolling an even number? Well, what's the probability of rolling a 2? 1/6. What's the probability of rolling a 4? 1/6. What's the probability of rolling a 6? 1/6. So we get 3/6. If you'll notice, our event had 3 simple events in it, and our sample space had 6. That's not a coincidence that the probability of our event is 3 out of 6. What's the probability of rolling a prime number? A prime number is any number bigger than 1 that's divisible by 1 and itself. So 2, 3, and 5 are prime numbers that are in our sample space. So the event of rolling a prime number would be the event of rolling a 2, 3, or 5. So 1/6, 1/6, and 1/6, we get 3/6 again. We have 3 simple events in our event of rolling a prime number and 6 in our sample space. So we get 3 out of 6. All right, what's the probability of rolling a number bigger than 5? Has to be bigger than 5. That event would be just 6. Has to be bigger than 5. So the probability of that event is 1/6. Our next example, our experiment is rolling 2 6-sided dice and observing the numbers that land facing upwards. Remember that our sample space is all those ordered pairs, 1, 1, 1, 2, and so on, all the way up to 6, 6. Okay, how many things did we have in that sample space? The number of items in our sample space was 36. Okay, what's the probability of rolling a sum of 4? You remember how we can get that event? It's either a 1, 3, a 3, 1, or a 2, 2. Okay, there are 3 items in there. So the probability of that event would be 3 out of how many were in our sample space? 36. Okay, some of you are going to ask, do I have to reduce that? You can. You can say that that's 1/12. But this is just fine for me. You can leave it as 3 over 36 if you want. What's the probability of rolling a sum of 11? So what was that event? To get an 11 was either a 5, 6 or a 6, 5. That's the only way you can get a sum of 11. There are 2 events, or sorry, yes, there are 2 things in that event. So the number in that event is 2, and the number in our sample space was 36. So the probability of rolling a sum of 11 is 2 out of 36. What is the probability of rolling a sum less than 13? Okay, sum less than 13. Wait a minute. If we add up all those, let me look at that. All these pairs. What's the biggest sum that we can get? Biggest sum is here at 6, 6, right? That's 12. So it's asking what's the probability of rolling a sum less than 13? That's the whole sample space. So the probability is going to be 36 out of 36, which is 1. That's a certain event. Remember, the probability of a certain event is 1. Okay, what's the probability of rolling a sum of 1? Well, the smallest sum you can get is when you add up 1, 1, which is 2. So that event is the empty set. And the probability of an empty set is 0. The probability of rolling a sum of 1 is impossible. That's an impossible event. Okay, number 3. Your experiment is drawing 1 card from a 52-card deck. Now remember, we had the ace of hearts, the 2 of hearts, the 3 of hearts, all the way up to Jack, King, Jack, Queen, King of hearts. And then we had all of them of diamonds, right? So there was the ace of diamonds all the way up to the king of diamonds. And then you had the black cards. You had the ace of spades all the way to the king of spades. And then you had the clubs, the ace of clubs, all the way to the king of clubs. All right, that's your sample space. How many things are there in a 52-card deck? You got it. There's 52. All right, what is the probability of drawing an ace? Well, how many aces are there? So that event is the ace of hearts, the ace of diamonds, the ace of spades, and the ace of clubs. There are 4 things in that event, and there are 52 things in our sample space. So the probability of drawing an ace is 4 out of 52. What's the probability of drawing a heart? So now we're just looking at the hearts. So the hearts, remember, we had ace all the way up to jack, queen, king. And if you'll remember, there's 13 hearts. So the probability of drawing a heart would be 13 out of 52 cards. One more. What's the probability of drawing a face card? Now remember, a face card is just a jack, queen, king. Jack, queen, king of hearts. So those are all of hearts. A jack, queen, king of diamonds. A jack, queen, king of spades. And a jack, king, queen of clubs. All right, that's our event. How many cards are in our event? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 cards in our event. There's 52 cards total. So the probability of drawing a face card is 12 out of 52. Now let's talk about the difference between theoretical probability and empirical probability. For theoretical probability, we use assumptions and deductive reasoning to assign probabilities to simple events. There are no experiments actually conducted. No experiments for theoretical. For empirical probability, we assign probabilities to simple events based on the results of actual experiments. So we actually do the experiment. The example, tossing one coin and observing heads or tails. The sample space would be H or T. The theoretical probability of tossing a tail, the event would be just T, and the theoretical probability of our event would be 1 out of 2. That's the theoretical probability. Suppose that you tossed a coin 500 times and heads appeared 330 times. So the number of heads is 330. You tossed it 500 times, so that means the number of tails was 500 minus 330, which is 170. Now they're wanting to know what is the empirical probability of tossing a tail. So the empirical probability of tossing a tail would be 170 out of 500. And I guess for notation, up here, if you wanted the probability of tossing a tail, it would be 1/2. And get rid of the E for the event. The probability of getting a tail is 1 out of 2. That's the theoretical probability. The empirical probability is the actual experiment that was conducted. There were 170 tails out of a total of 500 tosses. A equally likely assumption. Definition: if we assign the same probability to each simple event in the sample space, then we are actually making the assumption that each simple event is as likely to occur as any other. This is called an equally likely assumption, and we've already seen that up above. If we have n events in our sample space, then the probability of an event is going to be 1 out of n. Okay, we have a theorem that says, given the theorem is the probability of an arbitrary event under an equally likely assumption. Say that 10 times real fast. Okay, if we assume that each simple event in a sample space S is as likely to occur as any other, then the probability of an arbitrary event E in the sample space is given by, and this is what I told you up above in a previous example, it's no coincidence. The probability of an event is the number of elements in the event divided by the number of elements in the sample space. Some examples. The experiment, we're going to draw 5 cards from a standard 52 card deck. So that sample space are going to be all those 52 cards. What's the probability of getting 5 spades? Okay, the event. How many things are in that event? Let's break this down. How many ways can we get 5 spades? There are 13 spades, and we want to choose 5 of them. So we want the combination of 13, choose 5. How many things are in our sample space? There are 52 cards in our sample space, and we need the combination of 52, choose 5. Saying that one more time. The probability of getting 5 spades is equal to the number of ways of getting 5 spades, which is a combination of 13, pick 5, over the number of ways to pick 5 cards. And there's 52 cards, we need to pick 5. So we're going to go do 13 combination pick 5 over 52 pick 5. So that probability, we've got some scientific notation coming in. When you see e to the -4, you've got to move the decimal place 4 to the left. So you go 1, 2, 3, 4. Okay, so we have 4.95. 4.95 times 10 to the -4. That's going to be 0.000495. That's the probability of getting 5 spades. What's the probability of getting 5 face cards? Okay, how many different ways can we get 5 face cards? There are 12 face cards. Remember, Jack, King, Queen of all 4 suits? So there are 12 face cards. You want to pick 5. And the total number of ways of picking 5 cards from a standard deck is 52, pick 5. So we need to go change this to 12. 3.05. We got 3.05 times 10 to the -4. Is that right? Yes. So that's going to be 0.000305. Okay, what's the probability of getting 5 non-face cards? Okay, this is the probability of getting 5 face cards. The probability of not getting 5 face cards, in other words, the probability of getting 5 non-face cards, would be 1 minus that probability. So we want to do 1 minus that previous answer, and we would get 0.9997. Let's actually go out a little bit more, 0.999695. So your probability of getting 5 non-face cards in a 5-card hand is 99.999. .9695%. That's a pretty high probability. Last example. A club has 12 men and 16 women. A committee of 6 must be chosen. What's the probability of choosing 3 men and 3 women? Okay, for the men, you have to choose 3 men from the 12 men. How do you choose 3 men from 12 men? It's the combination of 12, pick 3. I don't like that being there. All right, how do you choose 3 women from 16 women? It's the combination of 16, pick 3. Now, how many ways can we get a committee of 6 people from all those men and women? There's 28 people to choose from, and you have to pick 6. So that's a combination of 28, pick 6. So here we go. Fraction. 12, pick 3, times 16, pick 3, over 28, pick 6. And as a fraction, let's see, let's just type it in. 880 over 2691. I get 0.3270. That's it. It is time to go practice. I encourage you to do this homework pretty quickly after you watch this video, and write everything down. This stuff it can get very jumbled very quickly. So keep your notes beside you while you're practicing and working on the homework. And until next time, have fun.